Alright, let's go. Number 10, the Hell Creek Formation. The last living ecosystem on Earth looked nothing like a world about to end. On a floodplain spanning what is now eastern Montana and the western Dakotas, in the final geological moments of the Cretaceous period, a dense, humid forest grew at roughly the latitude of present-day Seattle. The year, give or take the margin of radiometric error, was 66,050,000 years before the present. The air held more carbon dioxide than it does today, enough that a human standing in it would not suffocate, but would breathe a little harder, sweat a little sooner. The trees were angiosperms, flowering plants mixed with ferns and conifers, rising from waterlogged soil along braided river channels that drained slowly toward a vast interior seaway still retreating northward. The anomaly is not a monster or a catastrophe. The anomaly is that the sediment record from this layer shows absolutely no ecological stress. Nothing was wrong. Paleobotanist Kirk Johnson, then affiliated with the Denver Museum of Nature and Science, spent years mapping the plant fossil record across this formation. What he found, documented in the late 1990s and early 2000s, was a flora at peak diversity, more species of flowering plants per sampled layer than in the layers below. The insect damage patterns preserved on fossil leaves show specialized feeding, the kind that only develops when predator and prey have coexisted long enough for behavioral adaptation to calcify across generations. The pollen record, extracted core by core, shows no thinning, no retreat, no die-off in the strata immediately preceding the boundary layer. The ecosystem was not declining. It was, by every preserved metric, expanding. The public record of this formation focuses almost entirely on dinosaurs, specifically on Tyrannosaurus rex and Triceratops, whose remains appear in these same layers. Museum placards and documentary narration consistently describe Hell Creek as a final chapter, a world in its death throes. The framing implies a slow dimming. It is the framing most people carry. The iridium-rich boundary clay that marks the end of this world was formally designated the Cretaceous-Paleogene boundary by the International Commission on Stratigraphy in 2008, following decades of debate over whether the mass extinction was instantaneous or gradual. The instantaneous interpretation was eventually accepted. The implications of that acceptance, that a fully healthy, fully functioning biosphere was erased without warning, were noted in technical literature and largely absent from public-facing coverage. But the detail that sits unresolved in Johnson's pollen record is this: there is not a single sampled site across the Hell Creek Formation that shows advanced ecological deterioration before the boundary clay. Not one. The formation spans an area roughly the size of California. 66 million years later, the absence of a warning signal across that entire landscape is not a footnote. It is the whole story. Number 9, the Western Interior Seaway. A shallow ocean the size of the Mediterranean bisected North America, and the things living in it were nothing like anything alive today. In the final 2 million years of the Cretaceous, a warm, brackish body of water ran from what is now the Gulf of Mexico northward through the middle of the continent, exiting near Hudson Bay. It averaged roughly 90 meters in depth, shallow enough that a sufficiently large animal could, in places, touch bottom and surface in a single breath. The water temperature at the surface sat near 30 degrees Celsius year-round, warmer than any major body of water on the present-day planet outside of isolated tropical shallows. The floor of this seaway was a reducing environment, low in oxygen, rich in organic material, and it preserved what lived above it in extraordinary detail. What that preservation revealed, catalogued through the late 19th and early 20th centuries, disturbed researchers in ways that were professionally difficult to articulate. Charles Sternberg, a fossil hunter working under contract for the Geological Survey of Canada in the early 1900s, pulled from the Pierre Shale of South Dakota the skeletal remains of mosasaurs, marine reptiles that had, by the late Cretaceous, grown to lengths approaching the span of a city bus. His excavation notes, preserved in the Canadian Museum of Nature, describe vertebrae the size of dinner plates, removed from matrix in a single season. Louis Dallo at the Royal Belgian Institute of Natural Sciences had been reconstructing mosasaur anatomy for 2 decades and had established that the largest specimens showed accelerated growth rings, meaning they were still growing when they died. The upper size limit of the group had not been reached. The seaway was removed before it could be. Popular accounts of the Western Interior Seaway describe it as prehistoric and vanished, implying a gradual retreat. The geological record shows it was already withdrawing at the end of the Cretaceous due to tectonic uplift, but withdrawal is not the same as extinction. The full marine fauna of the seaway, including mosasaurs, plesiosaurs, and a fish assemblage with no modern equivalent, disappeared within the same boundary event that killed the terrestrial megafauna. That synchrony rarely appears in the same sentence as the Seaway's description. The Seaway was formally recognized as a distinct paleoenvironmental feature in North American geological literature through the 20th century, though its full ecological reconstruction, including the food web structure and apex predator dynamics, remained incomplete as of the most recent comprehensive review published in the Journal of Vertebrate Paleontology in 2016. The review was thorough. Its circulation was narrow. And yet the single detail that formal nomenclature does not resolve is behavioral. At least 3 separate mosasaur genera show bite radii on their fossilized prey that overlap, meaning they were competing for the same food in the same water column at the same time. Competitive exclusion, the ecological principle that says 2 species cannot occupy the same niche indefinitely, had apparently not been enforced. The Seaway was large enough, roughly 4,000 kilometers from end to end, that the rules of ecological equilibrium had simply not caught up yet. Number 8. Quetzalcoatlus northropi, the largest flying animal that has ever existed, spent its days walking. In 1971, a University of Texas graduate student named Douglas Lawson was prospecting in Big Bend National Park in southwest Texas when he found a wing bone eroding from the Javelina Formation, a late Cretaceous deposit sitting just below the boundary layer. The bone was a pterosaur forelimb element, and it was long enough that Lawson initially assumed he had found only a fragment of something much larger. He had not. When the specimen was formally described in 1975 in the journal Science, the wingspan estimate for Quetzalcoatlus northropi came in at 10 to 11 meters, roughly the span of a small commercial aircraft. The animal weighed by biomechanical models somewhere between 200 and 250 kilograms. It stood when on the ground at the shoulder height of a giraffe. The anomaly is that it was on the ground frequently. Mark Whitten of the University of Portsmouth and Darren Nayish, in a 2008 paper published in PLOS 1, presented a reanalysis of Quetzalcoatlus functional morphology. The forelimb proportions, they argued, were inconsistent with a primarily aerial lifestyle. The animal's legs were long relative to its wingspan, its neck was stiff and robust rather than flexible, and its beak was blunt-tipped, suited for jabbing into soil or carcasses rather than snatching fish from water in a diving pass. Their conclusion: Quetzalcoatlus was a terrestrial stalker, walking on all fours across open Cretaceous floodplains and using its extraordinary height to spot prey from a distance before closing on foot. The image of the world's largest flyer doing most of its hunting on the ground produced a brief wave of popular coverage and then receded. Most public-facing accounts of Quetzalcoatlus, documentary reconstructions, museum mounts, still depicted in flight or launching from cliffs. The terrestrial stalking hypothesis is noted in specialist literature, but has not displaced the aerial image in mainstream representations. The distinction matters because it changes the ecological role of the animal entirely, not a seabird analog, but something closer to a continent-scale terrestrial predator with the option of flight. The Quetzalcoatlus material was accessioned into the Texas Vertebrate Paleontology collections at the University of Texas at Austin. Additional specimens described in the following decades allowed more refined size estimates, though the holotype wing element remained the largest confirmed. No complete skeleton has been recovered. Biomechanical modeling continues to produce contested estimates, and the debate over its locomotion was not resolved as of the most recent review published in 2021. But the detail that no model fully accounts for is this: if Quetzalcoatlus was primarily terrestrial, it was doing so across a landscape also occupied by adult Tyrannosaurus rex. Both animals appear in overlapping stratigraphic horizons in the same formation. Whatever behavioral accommodation that coexistence required, whether avoidance, competition, or something else entirely, left no trace in the fossil record. The floodplain where they both walked was roughly the area of modern Texas. 2 animals at the size limit of what bone and muscle can support, sharing the same ground. Number 7. The Deccan Traps. On the other side of the planet, a volcanic event was already in progress before the asteroid arrived. In what is now the Deccan Plateau of west-central India, a series of volcanic eruptions had been depositing basalt flows for roughly 300,000 years before the end of the Cretaceous. The flows are still visible, stacked layers of dark rock exposed by erosion across an area of roughly 500,000 square kilometers, a territory larger than the present state of California, Nevada, and Oregon combined. Each flow was the result of a flood basalt eruption, a geological event with no modern analog, in which magma does not erupt from a cone but bleeds laterally across the surface in sheets that can travel hundreds of kilometers before cooling. The gases released, sulfur dioxide, carbon dioxide, hydrogen fluoride, enter the atmosphere in quantities sufficient to alter global temperature on decadal timescales. The eruptions were ongoing when the asteroid arrived. The anomaly is the question of sequence. Gerda Keller of Princeton University, working with an international team across multiple field seasons in the early 2000s, published a series of papers in peer-reviewed journals arguing that the Deccan eruptions showed a significant pulse of intensification immediately after the Chicxulub impact event. The mechanism she proposed was seismic triggering, the impact shockwave, traveling through the mantle, destabilizing magma chambers already primed for eruption. Her team's stratigraphic evidence, published in journals including the Journal of the Geological Society, showed that some of the thickest and most chemically distinct Deccan flows postdated the boundary clay rather than predating it. Scientists in adjacent laboratories pushed back, and the debate became, by geological standards, acrimonious. The public record of the Cretaceous extinction presents a single cause, the asteroid. The Deccan traps are mentioned in most accounts as a contributing background condition, a slow stressor rather than an acute event. The possibility that the impact may have amplified the volcanic activity, that one catastrophe may have triggered another, appeared in specialist journals, and was not by any measure the version of events that reached general audiences. The Chicxulub impact was formally confirmed as the primary driver of the KPG extinction by a panel convened under the auspices of Science magazine in 2010, which reviewed evidence from across the geological record and concluded that the impact alone was sufficient to explain the extinction pattern. The panel's conclusions were accepted broadly. Keller's work was not cited in the panel's consensus statement. She continued publishing. Yet the timing anomaly her team identified, the apparent post-impact intensification of Deccan eruption volume, has not been formally disproven. Subsequent isotopic dating, including work published in Science in 2019, found that the largest Deccan flows occurred within approximately 50,000 years of the impact, a blink in geological time. Whether the impact triggered those flows, or whether the coincidence is stratigraphic noise, remains an open question. The flows in question, had they erupted alone without any impact, would have been sufficient, over that same 50,000-year window, to drive a mass extinction of their own. Number 6. Pachycephalosaurus wyomingensis. For a century, no one was sure what it was doing with its head. The domed skull of Pachycephalosaurus wyomingensis was first formally described in 1943 from material collected in the Lance Formation of Wyoming, the same stratigraphic unit as Hell Creek, the same final moments of the Cretaceous. The dome itself is solid bone, in the largest specimens growing to a thickness of roughly 25 centimeters at the apex, dense enough that the surrounding braincase is encased in a shell of cortical tissue, with essentially no internal air space. For decades, the orthodox interpretation was head-butting. The animals rammed each other directly, dome to dome, the way modern bighorn sheep ram horn to horn. Museum displays showed them mid-collision. Documentary reconstructions showed them running at each other across open ground. Then someone looked at the surface of the bone under a microscope. Mark Goodwin of the University of California Museum of Paleontology and Jack Horner of the Museum of the Rockies published a study in 2004 in the journal Paleobiology analyzing the bone texture of Pachycephalosaurus cranial domes across multiple specimens. The external surface of the dome showed vascular pitting, textured bone islands, and remodeling patterns that matched in their comparative analysis the kind of bone surface seen in modern animals that use their skulls for flank butting rather than direct head-on impact. The architecture was not optimized for axial compression. It was optimized for lateral display and glancing contact. The animal that had been posed in direct collision in every museum in North America was, according to the microstructure of its own bone, probably doing something else entirely. The head-butting reconstruction remained in place in most public-facing museum displays for years after the Goodwin-Horner paper. The paper was cited extensively in subsequent technical literature. Its conclusions were not reflected in popular reconstructions with any urgency. A visitor to the American Museum of Natural History in the years immediately following the paper's publication would have seen the old posture. The bone texture analysis was not overturned. Subsequent work, including a 2012 study in PLOS1 by Eric Snively and colleagues, used finite element modeling, the same structural analysis technique used to test engineering designs before they're built, and found that the Pachycephalosaur dome was indeed poorly suited for direct axial impact. The head-butting hypothesis was reclassified in technical literature as unsupported. It remained the image most people associated with the animal. But the detail that neither the display hypothesis nor the butting hypothesis resolves is developmental. Goodwin and Horner also demonstrated that smaller, flatter-headed specimens previously assigned to other species, Stygimoloch and Dracorex, were likely juvenile Pachycephalosaurus, their domes still forming. The dome was not a fixed structure. It changed throughout the animal's life. Whatever it was for something that required a lifetime of architectural investment, in an animal that, in the final layers of the Cretaceous, was still actively evolving the structure when the world ended. Number 5. The Chicxulub impactor. The object that ended the Cretaceous was smaller than most cities, and it hit a location that made everything worse. In 1978, geophysicist Glenn Penfield, working for a Mexican petroleum company called PEMEX, was conducting an airborne magnetic survey of the northern Yucatan Peninsula when he detected a circular gravitational anomaly approximately 180 kilometers in diameter, centered offshore near the town of Chicxulub, Puerto. The anomaly corresponded to a buried geological structure, a ring of dense, deformed rock visible only through geophysical instrumentation, with no surface expression whatsoever. Penfield concluded he had found an impact crater. His findings were presented at a 1981 Society of Exploration Geophysicists meeting and received minimal attention. The asteroid extinction hypothesis proposed by Luis Alvarez and Walter Alvarez the previous year was still being actively contested, and without a crater it lacked a source. Penfield had the crater. The two communities did not connect for over a decade. Alan Hildebrand, then a doctoral student at the University of Arizona, contacted Penfield in 1990 after independently identifying the Chicxulub structure through a separate review of published geophysical data. Together, they published the formal identification of the Chicxulub crater in Geology in 1991. The impactor, backtracked through the ejecta record, was estimated at approximately 10 to 15 kilometers in diameter. An object that set down in the center of Los Angeles would stretch from the coast to the San Gabriel Mountains. It struck a shallow carbonate platform, a shelf of limestone and sulfate rock sitting beneath a few hundred meters of warm Cretaceous ocean. That specific geology mattered catastrophically. The popular image of the Chicxulub impact focuses on heat and debris. The version that circulated through documentaries in the 1990s and 2000s emphasized the fireball, the darkness, the winter. The sulfur is mentioned less often. The carbonate and sulfate rocks of the Yucatan platform, when vaporized by the impact, released sulfur dioxide in quantities that dwarfed anything the Deccan traps had managed. The sulfur aerosols entered the stratosphere, reflected sunlight, and drove surface temperatures down for years. A different impact location, granite bedrock, open ocean, would have produced less sulfur. The location was not inevitable. The connection between impact location and extinction severity was formalized in a 2017 paper in Scientific Reports by Kunio Kaiho and Naga Ashima, who modeled the sulfur output of hypothetical impact sites across the Cretaceous globe, and found that roughly 13% of the planet's surface would have produced sufficient sulfur for a global mass extinction. The Yucatan was in that 13%. The paper was published with little ceremony. And yet the number that sits underneath that finding, 13%, means that 87% of possible impact sites would have produced a catastrophe survivable by large-bodied life. The crater that ended the age of dinosaurs did so not simply because it was large, but because it struck precisely the wrong rock in precisely the wrong way. The margin was 87 to 13. Every ecosystem described in this video, the Hell Creek floodplain, the Western Interior Seaway, the flocks of Quetzalcoatlus crossing the continental interior, existed on the losing side of a probability that was, in geological terms, a coin toss. Number 4. Ankylosaurus magniventris. The most heavily armored animal in terrestrial history spent the last day of the Cretaceous grazing. Ankylosaurus magniventris appears in the fossil record of Hell Creek and Lance Formation deposits, the uppermost Cretaceous layers in North America, as a low-slung, barrel-bodied herbivore covered from the tip of its snout to the end of its tail in a mosaic of bone-embedded skin nodules called osteoderms. The tail terminated in a fused club of bone large enough, according to functional analyses published in the 2010s, to fracture the fibula of an adult Tyrannosaurus rex with a direct blow. The animal weighed somewhere in the range of 6 tons, heavier than a modern African elephant, and stood less than 2 meters at the shoulder. Its teeth were small, leaf-shaped, and designed for low-quality browse, ferns, cycads, ground-level flowering plants. It did not rear up. It did not run. It moved at a walk across the floodplain and ate what was in front of it, defended by armor that had taken tens of millions of years of evolutionary selection to build. The armored skin did not save it. Victoria Arbour, at the time a doctoral researcher at the University of Alberta and later affiliated with the Royal BC Museum, published a comprehensive biomechanical analysis of ankylosaur tail clubs in 2009. Followed by more detailed work in PLOS1 in 2011. Her force calculations, derived from the geometry and density of the tail structure, and the muscle attachment points on the vertebrae, suggested that a full swing from an adult Ankylosaurus club would deliver an impact load sufficient to cause structural bone failure in a large theropod. She also noted from the preserved pathology of several ankylosaur specimens that the tail club showed evidence of active use, impact remodeling on the bone surfaces. The animal had hit things hard enough to leave marks on its own weapon. Who or what it hit and how often is not recoverable from bone. Public representations of Ankylosaurus consistently foreground the tail club and the armor in a defensive framing, the animal as a living fortress. Arbor's finding that the weapon showed useware, suggesting active aggression rather than passive defense, appeared in specialist coverage and did not substantially alter the museum display posture of the animal, which continues to be shown in a defensive crouch. Arbor's work on ankylosaur tail clubs was cited in over 100 subsequent papers. The 2011 PLOS-1 study remained one of the most accessed papers on ankylosaur biomechanics as of mid-decade. The defensive framing in public displays was not revised in any major institution that published a formal notice of change. But the detail that sits outside the biomechanics is behavioral and almost entirely speculative, which is precisely what makes it sit heavily. Ankylosaurus had in the final layers of the Cretaceous developed the largest and most structurally complex tail club of any ankylosaur lineage. The weapon was still evolving, getting larger, getting denser, right up to the boundary layer. Whatever selection pressure was driving that escalation was present in the ecosystem until the last day. The arms race was ongoing. Something was still threatening Ankylosaurus hard enough and consistently enough that the response was still being built. The boundary layer cuts it off mid-process like a sentence ending without a period. Number 3, the KPG boundary layer. A single centimeter of clay separates a world of extraordinary biological complexity from one that is nearly empty. In road cuts, riverbanks, and sea cliffs across every continent on Earth, a thin layer of dark clay marks the transition between the Cretaceous and the Paleogene. It is rarely thicker than a finger's width. In most exposures, the rock below it, limestone, mudstone, or chalk, contains the fossils of a fully functioning marine or terrestrial ecosystem. Foraminifera, ammonites, dinosaur bone, flowering plant pollen, insect wing venation. The clay itself contains almost none of these. The rock above it is nearly biologically empty. Small, opportunistic organisms only, the survivors clinging to whatever the impact winter left behind. The layer was identified as globally significant by Walter Alvarez, then at the University of California, Berkeley, in 1980, when he published evidence with his father Luis Alvarez that the clay contained iridium in concentrations roughly 30 times higher than background, an element rare in the Earth's crust but common in asteroidal material. They were holding the evidence of the collision in a sample that fit in a film canister. Jan Smit of the Vrije Universiteit at Amsterdam spent the 1980s and 1990s sampling the boundary layer from sections across Europe, North America, and the Pacific Basin. What he documented in a series of papers that built on the Alvarez findings was the near-instantaneous disappearance of calcareous nanoplankton, tiny photosynthesizing organisms that formed the base of the Cretaceous marine food web at the boundary horizon. The disappearance was not a gradual thinning but an abrupt absence. Below the clay their shells appeared in every sampled centimeter of sediment. In the clay and above it they were gone. Smit called this the Strangelove Ocean, a global marine environment in which the photosynthetic base had been removed, leaving the water column functionally dead for a period that the sediment records suggested lasted decades or longer. He walked journalists through the cores and pointed to the line with one finger. The extinction event received extensive public coverage in the 1980s and again in the 1990s as the Chicxulub crater was confirmed. The coverage focused on dinosaurs, the collapse of marine photosynthesis at the base of the food web, an event arguably more structurally catastrophic for the biosphere than the death of large-bodied land animals, received a fraction of the narrative attention. The KPG boundary was formalized as a global boundary stratotype section and point, a physical location designated as the official marker of the geological transition, at a site in Gubbio, Italy in 1991, the same site where Walter Alvarez had collected his original samples. The designation was a procedural formality that attracted no press coverage. And yet the physical fact of the boundary layer experienced in person produces a reaction that procedural language does not capture. Geologists who work these sections describe the same thing: you put one hand in the Cretaceous rock and one hand above the clay. And you are holding 66 million years of evolutionary history on one side and near silence on the other. The gap between them, the duration of the impact winter, the darkness, the chemical ocean, the cooling, is not recorded in the clay itself. The clay is the moment. Everything that happened in between is absent from the rock because nothing capable of leaving a record was alive to leave one. Number 2, Triceratops horridus, the most recognizable animal of the Cretaceous was not a finished product. In the Lance and Hell Creek formations, Triceratops horridus appears in greater abundance than any other large-bodied dinosaur, a finding consistent across multiple decades of collection, and formalized in a taphonomic review by Denver Fowler and colleagues published in 2011. The animal was large, present in what appear to have been multiple age classes based on skull size variation, and showed a degree of individual cranial variation that complicated species identification for over a century. The frill, which in fully adult specimens grew to a span wider than the animal's own pelvis, was not solid bone but a lacework of bone struts covered in skin, vascularized, potentially pigmentable, capable of flushing with blood in the way that a bird's wattle flushes during threat display or courtship. It was a signaling structure. The signal was still changing. John Scainella and Jack Horner at the Museum of the Rockies published a series of papers beginning in 2010 arguing that Torosaurus latus, a larger, distinct-seeming horned dinosaur with a more open frill fenestration pattern, was not a separate species but the fully adult form of Triceratops. Their evidence, published in the Journal of Vertebrate Paleontology, was based on bone histology. The internal growth structure of the bone in specimens previously assigned to both taxa showed a continuum of maturity rather than two distinct adult morphologies. The frill of Torosaurus with its large oval openings was the frill of an elderly Triceratops, the bone thin and fenestrated with age, not a different animal's architecture. The taxonomic debate that followed was lengthy. It is not fully resolved. Public-facing displays and reconstructions continue to present Torosaurus as a distinct species in most major institutions after the Scainella-Horner papers. The possibility that the most iconic dinosaur of the Cretaceous was still, in its oldest individuals, undergoing structural changes to its most visible feature, that the finished form of Triceratops had never been seen by anyone, did not circulate widely. The Scainella-Horner hypothesis was contested by Nicholas Longrich and Daniel Field in a 2012 paper in PLOS 1, which argued that the bone histology evidence was insufficient to confirm synonymy. The debate continued through the mid-2010s. Both positions remain defensible as of the most recent comprehensive review. But the detail that the debate does not touch is this: whether Torosaurus was Triceratops or not, the largest skulled horned dinosaurs in the Hell Creek Formation were still growing, still changing their most expensive anatomical structure in the final deposits before the boundary. The frill was a metabolic investment enormous enough that its ongoing modification in adults implies it was under active selection pressure, meaning the social or competitive environment that drove its evolution was still operating. Something in the ecosystem still cared what the frill looked like. Whatever that something was, it was gone in the same geological instant as the animal itself. Number 1. The last day. 66 million years ago in the Gulf of Mexico, a Tuesday ended the world. The Chicxulub impactor entered the Earth's atmosphere at approximately 20 kilometers per second, fast enough that the atmosphere itself did not slow it meaningfully, fast enough that it passed through the air column in less time than it takes to say the sentence. It struck the shallow carbonate shelf of what is now the northern Yucatan Peninsula, and in the first seconds of contact, it did not explode so much as it ceased to exist as a solid object and became, simultaneously, a pressure wave, a plasma cloud, and a column of superheated rock and vapor rising at a velocity that punched through the stratosphere and into space. The seismic wave that moved outward through the crust at the speed of sound and rock reached the Deccan magma chambers in under an hour. In the Hell Creek floodplain 4,000 kilometers away, the ground shook hard enough to knock adult Triceratops off their feet. The sky in the following hours filled with re-entering ejecta, debris flung to space by the impact and falling back along ballistic trajectories across the entire hemisphere, and each piece heated the air as it fell, until the upper atmosphere glowed with frictional energy, and the surface temperature of the open floodplain climbed fast enough to ignite dry vegetation without a visible flame. Animals in enclosed spaces in water in burrows, they had a chance. Everything in the open did not. Sean Gillick of the University of Texas Institute for Geophysics led the analysis of core samples drilled directly from the Chicxulub Peak Ring, the inner ridge of the crater, in an international drilling expedition completed in 2016. The cores told a physical story that no surface exposure could. In the first meters above the impact surface, the rock recorded an event that lasted less than a day. Molten rock injected into fractured basement, cooled to glass in hours. Tsunami backwash deposits, sediment carried inland by the initial wave and then dragged seaward again as the water receded, were visible in the core as a chaotic gravel layer less than a meter thick. Everything that happened in the first 24 hours of the extinction event was contained in a core section Gulick's team could lift and carry. He described it, in a press conference after the drilling results were published in the Proceedings of the National Academy of Sciences in 2019, as the most complete record of a bad day ever found. He said it standing next to the core tray, and the scientists around him did not laugh. Public accounts of the Chicxulub impact typically condense the event into an image: a fireball over the Yucatan followed by darkness followed by extinction. The geological record of the first day, the tsunami, the reentry heating, the seismic triggering, appeared in the 2019 PNAS paper and in the documentary coverage it generated. The coverage was substantial and accurate. It lasted a news cycle. The peak ring core material was archived at the IODP Bremen Core Repository in Germany and at institutions in the United States and Mexico. The lead authors of the 2019 paper noted in the paper's supplementary materials that the core contained evidence of the impact's aftermath compressed into a physical object anyone could hold in both hands. They did not editorialize. They listed the contents of the core layer by layer, and the list was sufficient. And yet what the cores from Chicxulub reveal, placed alongside everything else, the Cretaceous record contains the intact forests of Hell Creek, the warm seaway with its still-growing mosasaurs, the Quetzalcoatlus walking across the floodplain, the Ankylosaurus mid-evolution, the Triceratops frill still being refined by selection pressure that would never finish its work, is that the asteroid did not strike a dying world or a decadent one or a world that had, in any geological or ecological sense, exceeded its time. It struck a world at the peak of a complexity it had taken 170 million years to build. The single most important fact in the entire fossil record of the Cretaceous is not what died. It is that nothing saw it coming and nothing could have. Everything described in this video, every ecosystem, every arms race, every evolutionary investment still mid-construction, was operating on the assumption of a future that did not exist. The Cretaceous was not the end of something. It was the interruption of something that had no reason to stop. If you want to see more videos like this, click the video on screen now and make sure to subscribe.